Today, I have the pleasure of introducing Mike Headley and Dr. Jim Rankin. Mike Headley is the Executive Director of the South Dakota Science and Technology Authority and the Laboratory Director of the Sanford Underground Research Facilities, SURF, where he leads a 190-member team in the development and operation of the deepest underground science laboratory in the United States. He has more than 30 years of engineering and management experience and served in the United States Air Force for 6 years. Before coming to SURF in 2008, Mike served in various roles at the U.S. Geological Survey, Earth Resource Observation and Science Center, and was the Deputy Program Manager and Assistant Vice President for the Science Application International Corporation. And at both those U.S. Geological Survey and the Earth Resource Observation and Science Centers in Sioux Falls, South Dakota. He earned his bachelor's degree from South Dakota State University and an MBA from Loyola Marymount University in Los Angeles. I also have the pleasure of introducing Dr. Rankin. He is our 19th president at South Dakota Mine and a fellow alum of yours. He graduated with his electrical engineering degree in 1978. And with that, I would like to turn things over to Mike.
All right, thanks, Shelley. So good morning, everyone. Mike Headley, I'm the lab director up at SURF and the executive director with the South Dakota Science and Technology Authority. And I appreciate you welcoming an East River Jackrabbit to a West River Mines event. So thank you so much. And just wanted to also give a plug. Shelley mentioned the book signing that Steve Mitchell is doing up in Lade on Saturday. That'll be at the Sanford Lab Homestake Visitor Center, and I believe it starts at 1 o'clock. But we partnered with Steve on the development of that book, and it's fabulous. And so, would encourage you to come on up and have Steve sign one for you. And we make a little bit of money on that at the Visitor Center, so it's nice to get some funding to support what we're doing. So we're going to spend a little bit of time this morning. We're going to talk about SURF and some of the things that we're doing currently with the facility and science and what's being developed for the future. And then at the end, Dr. Rankin and I are going to walk through some slides talking about specifically what Mines is doing up at SURF from a science perspective and also engineering. So we'll also be able to give you some specific information about what students and faculty are doing today. So a bit of an overview of the South Dakota Science and Technology Authority. Our mission is really about doing two things. It's advancing world-class underground science and advancing or inspiring learning across generations. So we, in addition to doing the science nearly a mile underground, we also have a very strong K-12 and STEM public education and outreach program that I'll tell you about later. So at SURF, we have about 400 full-time staff. That includes 190 who are part of the South Dakota Science and Tech Authority team. And then we have a lot of construction activity going on with really one of the largest science experiments ever attempted on U.S. soil. And we'll talk more about that later in the presentation. But we have, as a result of that project, a lot of people from Fermilab who are managing that effort, and close to a couple hundred contractors who are working on that project. So the SDSTA, we are the owner and operator of SURF and supported the science, and we're really there to operate and maintain the facility and make sure that everything happening there is safe and getting people underground access to do their work and supporting the science. And and really in a range of disciplines, and we'll talk about that in a moment. Most underground labs in the world are primarily dedicated to physics, but we have truly a multidisciplinary program. So I mentioned this big experiment that we're working on. It is called, the facility side of it is called the Long Baseline Neutrino Facility, or LBNF, and the experiment is called DUNE, or the Deep Underground Neutrino Experiment. And as I mentioned, we'll talk more about that in a bit. And as I also mentioned, the K-12 and public STEM education and outreach. And our activities, we've been funded now since federal fiscal year 2012 by the U.S. Department of Energy, and currently that's through a 5-year cooperative agreement, which is basically, it's in essence, it's a contract, but it really is, it's kind of formed like more of a grant research agreement. So that's how we get our day-to-day funding to operate the facility. So I thought before we get too far into this, just to give you an idea of return on investment that the lab is bringing to the state. And so We were just in Pier this last session working to get $13 million for additional lab space built out at SURF, and spent a lot of time sharing these types of numbers with legislators. And the return on investment that the state has put in to SURF has really been impressive. So if you look at all the dollars that have been put in from the state, at total 62 million, now 75 with this additional 13 that's been approved. But as of the first part of this year, between federal and private sources, there have been 932 million invested. So in essence, a 15x return on investment, which I wish my 401k and IRA were doing that well. So it's pretty impressive what SURF is doing economically for the state, and we're very proud of that. As I mentioned, we have 400 FTE, and as part of this large neutrino experiment, LBNF Dune, this experiment's going to last for a number of years. It will take roughly 10 years to build and 20 years in operations at a minimum. So the Department of Energy is really making a 30+ year commitment to SURF in South Dakota. So we're very excited about that. So recently we updated our economic impact that we're tracking for this decade. And so if you add the first two columns together, you get in essence about $2 billion worth of impact, positive impact here, South Dakota statewide. And if you look at jobs benefitly or that are benefited by SURF being in the state, it's approaching 1,200, which is great. We're very happy about that. So let's talk a bit more about the facility. I know some on the line here are very familiar with SURF, but some are not. So we'll give a little bit of background. So what you see here in orange, this is our surface footprint up in Lead. And so 223 acres on the surface. And then in addition to that, we hold title to all the mineral rights underground that Homestake mined. And so that's roughly 7,700 acres in plan view. So the lab was created in 2007. And we benefited by just a great partnership with the state of South Dakota, as I've already mentioned, and Barrick Gold Corporation, who bought the Homestake mine years ago, and also T. Denny Sanford in the $70 million gift that he provided for us really to kick off the transition of 130 years of mining success into a new world-class research facility. And so, as I mentioned, we're funded by USDOE, and currently that's at about $35 million per year. So one of the questions I get asked a lot is, why do we go underground to do this work? And from a physics perspective, the big driver is getting to one of the quietest spots on the planet. And so as you see this animation, what we're trying to show is cosmic radiation coming from space, that if you try to operate these very sensitive physics experiments on the surface, that cosmic radiation would represent a huge noise source, such that you wouldn't be able to see the rare processes that we're trying to observe. And it would be kind of like trying to listen to a pin drop at a Rolling Stones concert. It just wouldn't work. And so by going nearly a mile underground, it lowers that background radiation by about a factor of 10 million. And so while there are still a few cosmic rays that get through, it blocks the majority of those. So that with the additional shielding techniques, we're able to actually perform the science deep underground. So that really is the main driver and why we bother to go a mile underground to do this work. So as we go a mile underground, we have science that's located in a number of locations underground, but the experiments that we tend to talk the most about that are really on the larger scale from a size and also the number of people involved are the physics experiments. And so as we go to the 4850 level, or 4,850 feet underground, at the base of, well, we have two shafts that we operate, the Yates and the Ross, and they go down and intersect with the 4850 and end at about the 5,000 foot mark. But over on the left, we see the Yates shaft and the Davis campus. This is an area that Dr. Ray Davis did some of the earliest work studying neutrinos from the sun, starting back in the 1960s. And Dr. Davis won a Nobel Prize in 2002 for the work that he did at Homestake. And so that campus is named after him. And so we have two main experiments over there, the world's leading dark matter experiment called LZ. And we'll talk more about the involvement of mines, faculty, and students, but a lot of really the major projects that we're going to talk about during this presentation have students and faculty from mines that are involved. And so the LZ, that's our main dark matter experiment. The Majorana demonstrator, this is an experiment trying to study a process called neutrinoless double beta decay and helping us trying to understand neutrinos and their role in the universe and how they operate. And then we also have a partnership with Black Hill State University called the Black Hill State Underground Campus, where we have a lab where we do what's called low background counting. And so I mentioned we go underground to get away from cosmic radiation. And so by going a mile underground, we don't want to take a lot of materials with us that are also giving off radiation as well. And so wouldn't be harmful for us as humans, but it would generate a noise source as part of the experiments. And so basically all the major components in these detectors have to be characterized before they're used. And that's what low background counting is all about. So if we go from left to right about 1 kilometer in distance to the west, we're over at the Ross Shaft. And we have a lab space called the Ross Campus. The majority of the activities on the Ross Campus are currently mothballed. And that's because we're excavating a large amount of rock for this LBNF dune experiment that you can see. So the graphic kind of gives you an idea of the scale in what we're operating today in blue versus what's in green. And so it gives you an idea that what we're constructing for the future is really much bigger than what we've been operating up to this point. So just to talk about the science program briefly, so starting in the upper left, we have the Lux Zeppelin dark matter experiment. This is the 2nd generation dark matter experiment that we've hosted, trying to be the first to directly detect particles of dark matter and help us figure out this roughly 80% of the mass in the universe, or the gravity in the universe, that we really don't know much about. And so the LZ experiment is the most sensitive dark matter experiment in the world. They've run for a short period of time. They haven't found dark matter yet, but they're doing it better than anyone else. And so we host them. Over on the right. We have neutrino experiments that we have at SURF, the Majorana demonstrator, which has had significant involvement from South Dakota mines. And as you can see, their cryostat there, copper components. Those copper components have been really grown underground, taking copper, off-the-shelf copper that you can buy in the open market, taking it underground and producing the world's most pure copper for the production of this experiment. And that's something that Mines is really had a leadership role in. And then I mentioned the LBNF Dune experiment, which is not completed yet, but is coming here over the next few years. Down in the lower left, we have biology. We've worked with a number of national labs around the US and major universities and NASA, and also universities here in South Dakota for doing some very interesting biology work underground. And in fact, one of the last rover that went up to Mars, one of the instruments that flew on that mission was actually brought to SURF and tested before it was mounted onto the Mars rover and launched. So that was pretty exciting. And then over on the right, we've really done a lot of geology related and engineering related works from the start. And I've been at SURF for about a decade and a half now. And even in the early days when we were trying to figure out the plans for the future, we were doing geology work underground. And a lot of that was in partnership with mines. And so what you're seeing there, this is an experiment called Sigma V. And it's a partnership of a number of US national labs that are trying to develop enhanced techniques for geothermal energy production in the future. So it was really a great group led by, or the main point of contact here in South Dakota, Dr. Bill Rogentine, who I'm sure a number of you know. He was part of that work. So the overall science program, and we're currently working with 29 different users. And with the addition of Dune, we're now over 2,000 collaborators that we work with. And you can see the dots all around the world representing where our users come from. And now over 200 institutions from 38 different countries. And in general, we have about 374 on-site users who are coming regularly. And then we have also some, well, that's current. And then from 2007 to present, approaching 700. But with the addition of Dune, that really adds close to 1,500 additional collaborators that we're working with at SURF. So I always get asked about applications and what comes of this. Besides science papers and Nobel Prizes, there are actual practical applications that have come from the work that has been done at labs really around the world doing this type of physics research. And so advanced manufacturing, beam welding, and sterilization types of applications for the food industry, medical imaging, when you go and you get an MRI to take a look at your knee that you're having troubles with, thank a particle physicist for the research they did to make that happen. A lot of work in computing has happened in the past with the development of the World Wide Web, and now we're hearing a lot about the advancements in quantum computing. And actually the high energy physics community is playing a huge role in the advancement of quantum sensors and also quantum computing. GPS and some of the original theories behind how GPS works were developed through physics. And then also some of the detectors that we're using, like the detectors used on the Majorana demonstrator experiment, those types of germanium detectors are being used for national security related applications as well, and tracking nuclear materials from the friendly side of a hostile border. And so there's definitely national security applications as well for the technology that comes out of this work. So let's talk about the LBNF Dune project for a few minutes. So this is the US Department of Energy's flagship neutrino experiment, and it includes the LBNF, which is the facility both at our location and also at Fermilab located at Chicago, and Dune, which is the suite of detectors that will go into the facility that will be studying properties of neutrinos. And so as you can see here, it involves two sites: Fermilab, which is located in Batavia, Illinois, just outside Chicago, and then SURF, which is located up in Lead. And the game plan, or the way this experiment will operate, will be Fermi has a particle accelerator that produces the most intense beam of neutrinos of any other accelerator in the world. And so they'll be directing a beam of those neutrinos through the Earth. There's not a tunnel or anything between here and Chicago, but the neutrinos go right through the rock mass between here and Fermilab. And as those neutrinos make that 4 millisecond flight, we'll be watching them change through that period. And neutrinos exist in, as we know, 3 different types of neutrinos. And as they fly through space, they change from one type to another. And the physics behind how that happens is really not fully understood. And so to kind of cut to the chase, what we're trying to figure out here through studying neutrinos is really why we live in a matter-dominated universe. The standard model of physics suggests that at the Big Bang, there was an equal amount of matter and its negatively charged counterpart, antimatter. They should have canceled each other out. There would be a bunch of light, and that would be it. But as we look around, we're made of matter. We live in a universe that is full of matter. And the physics behind how we got from A to B, from the Big Bang to here, is, like I said, not well understood. And that's what we're trying to figure out with this experiment. So this is a big group, close to approaching 1,500 collaborators, 280 or 18 institutions, 37 countries involved. And I've got a quick video showing the activity at SURF, so the actual development of the LBNF facility, and then the detectors that will go in those. So the construction activities for LBNF Dune really are focused over at the raw shaft. And so the measurements here are all in meters. This video was put together for a pretty international audience, including the US. So if you look at the area of the development, the excavation that will be created, it approaches an area 8 soccer fields. So we'll be excavating and are about 60% done in excavating 800,000 tons of rock and bringing that up and putting it in the open cut a bit north of us up in Lead. So after the caverns are completed, we'll be installing the 4 large detectors. You're seeing one of those. And each one of these will be filled with about 17 kilotons of liquid argon that will be used for detecting the neutrinos that are directed from Fermilab, and then measuring out signals that come from the recoil of the neutrinos interacting with atoms of the liquid xenon. So we have to keep this, I'm sorry, liquid argon. If I said xenon, that was incorrect. So this is liquid argon, and so the argon needs to be kept very cold, about 300 degrees below 0. And what you're seeing, this box is basically like a Yeti cooler on steroids. It's a steel box that has a meter of insulation in it, and then a stainless steel lining that helps keep the argon cold. So that's one of 4 detectors that will be fielded at the site. And the first 2 are currently funded, and the project Fermilab and DOE are working on funding for the final 2 detectors that will be installed. So here's the excavation, and it gives you an idea of the dimensions down in the lower right. So the 4 detectors will be in the 2 detector caverns, the north cavern and the south cavern. And then the middle cavern, the central utility cavern, will be where all of the support equipment is that keeps the argon cold, it keeps it pure, and all of the data acquisition equipment, really everything that's needed to support the operation of the detectors and capture the data and get it up the shaft to the surface where it's transported to various national labs and other international labs around the world. So the progress, if we kind of look at this in plan view from overhead, all of the connecting tunnels and drifts have been completed. And now we're into really the heart of the excavation of the caverns. And so about 60% complete at this point. And if we look at that from the side, you can see the 3 caverns. We're approaching about 1/3 of the way through the caverns in volume, maybe a little bit more. And so the plan is to, as you can see, where they started at the top, benching their way down towards the bottom. These will be approximately 90 feet deep when they're completed. And so the breaking of rock for LBNF will be completed by the end of this calendar year. And then there will be about a 6 to 8 month period of the installation of concrete, all the flooring in the drifts and also in the caverns. And then as we get into a bit more than a year from now, we'll see the installation of the infrastructure, power, fiber, HVAC, and all of the safety systems that would be installed on the caverns. And in parallel with that, the installation of the first 2 detectors. And so there's a big push on. There's a lot of competition between this experiment and one that's being developed over in Japan. And so the project is really working to optimize the schedule to try and get operational as quickly as possible. And so the plan is to get the first 2 detectors filled and start to go operational as we get into the 2028-29 timeframe. So a few pictures of the excavation underground. This is a video from a shot that was taken this last week. As we've got into the benching, they've really been able to ramp up the amount of volume that they're shooting at any given time. And so Tyson Mining is doing the excavation. They're doing a wonderful job. They've been a great contractor to work with. And so, so they're in the process of getting the excavation completed so that we can get that finished and then get on to the actual installation of the infrastructure. This is really a great photo from the North Cavern. You can see the jumbo drill over on the left-hand side, drilling out around for shooting that off and then being able to remove the rock. And then there's a small mucker, an LHD, large load haul dump over on the right-hand side. And so as the rock is shot and removed, you can see there's a gentleman standing at the far end of the cavern. So the LHD will go out that end, and then the rock dump to put rock into the skips or the buckets that bring the rock up from the underground are located over in the raw shaft. And so that's the muck gets rubber tired over to the shaft and then brought up and then conveyed on about a 4,000 foot long conveyor over to the open cut. And here's one of the drills that's been putting rock bolts into the ceiling or the roof or the back of these caverns. And hopefully you can see the worker kind of in the middle of the picture towards the bottom at scale. And so these are some of the largest underground mining machines that are made in industry today. And so trying to get these underground for our staff is a big challenge. Our cage, or the conveyance we use for taking people and materials in and out of the underground, is only about 5 feet wide by 13 feet long. And so a lot of this, really all this equipment either needs to be taken apart or cut apart to be able to take an underground and then put back together or welded back together. And then the work is performed, and then when we go to demobilize, the reverse will happen. So I like to say this job is it's literally building a ship in a bottle, and at a scale that's really really amazing. So we have a lot of other labs that are located in the world. We all work very, very well with them, and it's a very collegial environment, but it's competitive. Everyone is competing to get the world's best science at their lab. And so what this is showing is the volume of space that each lab has at depth. And so as you go further down on the chart from top to bottom, the depth gets greater. And then the larger like the Christmas tree ball is for each one, that indicates more volume of space. And so what we have at SURF right now, if you look over on the left, there's a darker dot in the middle that represents the Davis campus and the Ross campus. And then what we're excavating with LBNF will kind of be the next bigger ring. And then the next ring out from that will be some space that we're wanting to build in the future that I'll talk about in a moment. But our major competitors are Canada. Canada has a beautiful facility located up northwest of Toronto. The Italians have a lab that is a couple hours east of Rome. The Chinese are very big players in this game as well. They have built out a lot of space at great depth, and they're working hard to attract experiments. And then the Japanese have played a big role primarily in neutrino study work for quite a while, for a number of years. And so, as I mentioned, they're one of our main competitors between, for the Dune project. So while these science experiments are being developed and put underground, the community is trying to figure out what comes next. And so there was a strategic plan put together back in 2014 called the P5 report, or the Particle Physics Projects Prioritization Panel. Boy, that is a mouthful, isn't it? And they report to a federal committee commissioned by the Department of Energy called HEPAP, or the High Energy Physics Advisory Panel. And so HEPAP advises the agency on future directions in science. So every 10 years, the P5 report gets updated, and that process is going on right now. And so there was a lot of community input called there was a community summer study that was completed this last year up in July, which was really kind of the culmination of about 2 years worth of conversations over Zoom, but was done face-to-face, up in Seattle. And what came out of that were a lot of recommendations into the P5 committee who's writing this report. And we were very happy that from an underground facility perspective, we received a number of recommendations that were very supportive of SURF's future. And so you see these here at the bottom, basically leverage the work that's happening right now, the excavation work, to build out more space at SURF for other types of experiments. And we're working on that. I'll talk about that in a moment. And then designate SURF as a formal, what's called a US DOE user facility, or a facility that is really recognized at a national level as the deep underground science lab here in the US. So we're very pleased with that. We've been working with the P5 committee, and we're hoping to get strong recommendations out of the next strategic plan for future growth for SURF. So the additional space, I mentioned 13 million additional that we received from the state towards the beginning of the presentation. And this is really for a two-phase build out. So phase one will be the development of this tunnel that you see in yellow. And it will be basically right across the hall from LBNF Dune. That's so that we can get rock to the Ross shaft to bring it up from the underground. And so this tunnel will be developed in the first 6 months of next year. And we're very appreciative of the support from the South Dakota legislature and the governor for this funding. And so it allows us to get this tunnel completed kind of in the period between the transition from LBNF and it being kind of a dirty construction site to when Dune starts to install towards the latter half of next year. And then it provides the isolation and the ventilation and rock handling capabilities that we would need starting in roughly the 2027, 28 timeframe to come back on private money and build out additional space in this phase two area. And so these new caverns, and these may change. I mentioned this strategic planning process. We will be taking input from that. And so the dimensions and shape of these may change somewhat, but right now we're planning on 2 halls that are 100 meters in length. And so that's kind of our baseline right now as we go forward. But we're very excited about having the opportunity to build out additional space to hold a wide range of science into the future and be able to expand what we're doing. All right, at the beginning of this, I talked about K-12 STEM, E&O, and these are the main areas that we focus on. So we do a lot of presentations and field trips. We go out into the schools. This time of year, we get a lot, actually this week, we have been getting a lot of field trips, and next week, and as school is starting to wrap up for the year. And we have 17 unique curriculum units that have been developed that meet the current state science standards that provide really 5 to 15 hours of hands-on instruction for teachers to use. We have a number of internship programs located there in the third block. And then we do a ton of teacher professional development, and we've been averaging working with over 500 teachers in the state, providing really high quality professional development and helping them hone their skills to be able to better educate our kids in the schools here in the state. And that's branching out too. As our program has grown, we're really working now on how does this scale to more of a national and international level eventually. So a few numbers to show the number of students that we've worked with in each of these areas. So pre-COVID, we generally worked with about 12,000 students per year. Took a bit of a dip, although we still were quite active during COVID, and then have come back quite strongly. So almost 20,000 students last year. And we're not done this year yet, but we're already at almost 16,000 students that we've been working with. So very proud of the work that our E&O team has done. We have a visitor center. I mentioned Steve Mitchell's book signing. That'll be at the visitor center. And so that we developed this a number of years ago, and it was operated by a local nonprofit. And they had decided they kind of wanted to get out of the business of running the place. And so we acquired the ownership back January of last year. And this last year hosted over 54,000 visitors. And so if you're up in Lead, please come on up and check it out. It's really an amazing building, and the exhibits that we have are really tremendous and very interesting. And I think this is one of my last slides. So while we're doing all these other things, current and future from an experiment perspective, we've been dreaming big about developing an institute for underground science at SURF. And we're actually planning to kick this off at a smaller scale later this year in around the beginning of the fourth quarter of this year. But what we're really wanting to establish is a world-leading center for underground science collaboration and intellectual community. So in addition to holding the experimental work that we're hosting now, but being able to host theory-related workshops and conferences, and trying to provide really a strong intellectual community with a focus around underground science, not just the work that's being done at SURF, but what's really being done at a global scale. So provide leadership in long-term science community planning, engage the global community in figuring out the vision for long-term underground science, serving as a hub for information about underground science, and then fostering a close collaboration between the science and education and outreach. And what you see over on the right, this is a graphic trying to show you the various types of players who would be involved and the multidisciplinary nature of physics, life scientists, earth science, and engineering, a strong education and outreach program, and an inclusive environment that really is welcoming of anyone to come to SURF and do great work, no matter where they're from, what their background is, or what have you. So with that, that's the end of the slides that I have. I think I'm going to turn it over to Dr. Rankin. He's got a few slides to go through and talk about work that my students and faculty are doing at SURF. So I'll stop sharing.
And I'm here, and give me 1 second to share my screen and get rid of that piece. All right, is that coming through okay?
Yes, it is.
All right, thank you. As Mike said, SURF is underneath the South Dakota Science and Technology Authority.
I think you're muted, Dr. Rankin.
Oh. How about now? Is that working?
It is staying on your main page.
Well, let me try this again. You can hear me when I'm on this page, right?
Yep, I can hear you.
Me. Okay.
Yep.
Okay, so now let me share that screen again. How's that? That work?
Yes, I can hear you and see you.
All right, perfect. So, yeah, as Mike said, this SURF is underneath the South Dakota Science and Technology Authority, and the president of South Dakota Mines is an ex officio member of that authority.
Please proceed. It must be me.
Oh, and so I do get a chance to see what's going on up at SURF, and so there's definitely some exciting things. So that I don't embarrass myself with the science, most of my slides are going to talk about the faculty, staff, and students that are working up there. But I noticed when I look at the participants, we have a lot of them listening in. And so if you have questions, please email me and we'll make sure we send it to the people that can answer questions. And I've asked Mike to step in as well. So the first one here is CASPAR for Accelerator System for Performing Astrophysical Research. You can see faculty Frank Strider over here on the right. We've had 2 PhD thesis students in South Dakota Mines and 1 in preparation. and 10 undergraduates working on this particular project. And you can see it was jointly operated by South Dakota Mines and the University of Notre Dame. And then we've shut it down for Dune excavation. So that, I'm hoping to restart that back in early 2024. So and I will give these slides to Shelley and she can email them out to all of you because there's a lot more information on these slides than I can talk about. The second one is on the Majorana demonstrator. I got these from Cabadan Christofferson. I know Cabadan is listening as well. It talks about the research that they have going on. And I will jump to this next one. You can see Cabadan's name here, but all of the activities that are going on. And down at the very bottom, you get an idea of how many people have been working on this project since 2010. 24 undergraduates of many different disciplines. 2 out of the material sciences, engineering and sciences, master's students, and a PhD student that has gone through, and then another one getting ready to go on legend here. And there's a little bit of the legend activity shown on this particular cell with the electroforming and the different pieces that come in. I don't know, Mike, is there anything that you would like to add on this particular slide?
Well, we're happy to be, even though some of the future activities will be happening in other labs, we're happy to be working with Cabadan on the electroforming of copper going forward. And just to really note, Cabadan and her team really were the lead for the operations of this experiment at SURF, and so really was great to see a local institution take a huge leadership role, and along with Frank Streeter on CASPAR as well.
Okay, thank you. Here's the dark matter, the LZ. Richard Schnee is our department head in physics and our other faculty listed here. So we've got a lot of activity going on with LZ. Actually, I've got about 6 slides on LZ and I'm not going to go through all of them, but here's a slide talking about a couple of our students that are working on the project for LZ. This one's on the Undergroun Radon-Reduction system. This one we've got on the additional, actually I skipped one there. I'll switch that over to Dune, my mistake. And you can see Jurgen's picture up here and the work that he's got going on Dune, the deep underground neutrino experiment. And then you'll see a list of students that we have listed here as well. So exciting to see this Dune as this comes to fruition, as the caverns are being excavated and what the science is going to look like. Dr. Wying, again with Dune, some of the activity that he's got going on. Here's one on the UV light calibration and monitoring system. And you can see we've got a lot of different students involved in this particular project with mechanical engineers and physics together, and also some graduate students have been playing a part in the installation of technology over at CERN for the prototype over there. So not only doing things at SURF, but taking a role in this experiment outside the US as well. I'm going to switch here for a little bit. One of the things that's going on in this slide is the CAT Labs MindStar Consortium. And this is technology that will be up at SURF at the 1750 level. And this is a chance to test out some of the new mining equipment that's going on up there. It'll be a great, as it says, robotic mining equipment testing. And so glad to be part of that. You might think this is out of the mining engineering department, but this is really everybody because of automation. It involves almost every department we have on campus with the activity that CAT is looking at. So that's an exciting, a different perspective on what goes on up at SURF. And then I want to just end with mining engineering senior design projects. It's good to have our senior design teams working on activities up there. So you can see everything from how to repair the Oro Hondo exhaust shaft to this number 5, and then ventilation at the 1700 level, which is where the MindStar activity is working at. Again, more on the Oro Hondo. And then look at this one. This the bottom one is on what would it take to put in a new shaft. besides the Ross and the Yates. So some exciting activity there from our students. So you're seeing undergraduates, you're seeing master's students, you're seeing PhD students from many of our disciplines going on. And I know I talk completely over the science because that's not my area. And we have lots of experts that can answer any questions if those come in, because I did put my email in the chat box, but I did want to leave a lot of time for questions. I know we've already got a few in there. So let me back out of this, turn it over to Shelley to moderate the questions, and we'll go from there.
Thank you, Dr. Rankin. I think from those lines, the things I take from that the most is how amazing is it to be an undergraduate student here at South Dakota Mines and have the opportunity to work with SURF and do this kind of research. You just don't get this at every university. So that's pretty amazing to see. We do have a few questions. And Mike, I know we had some emailed to you earlier. Did you want to start with those questions or?
Sure. Yeah, I'd be happy to. So we did get a couple of questions ahead of time. The first was, what's the ideal temperature range for the experiments? And basically, I would say outside the cryogenic vessels that hold the detectors and so forth, it's really, we try and maintain the temperature at what you would expect to see in a lab, at really around room temperature. And one of our main concerns is the air that comes down underground has a lot of humidity in it, which is not very helpful for electronics. And so kind of drying out the air is really our main challenge, in using HVAC systems, off-the-shelf HVAC systems underground to do that. The next question was, are the lab facilities enclosed, or are they just using space from Homestake and the cavities of the tunnels dug? It's a little bit of both. And so the Davis campus was really kind of purposely excavated for neutrino work back years ago, and then we've expanded it. But I would say over at the Ross campus, we took existing Homestake shops and basically walled them off and improved them and made them into lab space. And so the long-term plan for experiments, I think, just in general, the long-term plan really in all these disciplines is different. Each different science group from a broader perspective has to set the vision of where they want to go and what they want to do underground. And so we try and stay in contact with all those various groups to understand what the needs are long-term to hope that we can support what they're wanting to do underground. So I think that was it for the pre-questions.
Excellent. We do have a few questions in here. One person, Jim, asked, what is the ultimate goal of the experimentation? And I believe it was when you were talking about, this came in when you were talking about the layers, when you're doing like the neutrino capturing and seeing what's out there, if I have that correct, Jim.
Yeah, I guess the ultimate goal, it varies by experiment in each discipline. They all have the big science questions that they want to answer, and those drive the experiments and in a hope to answer those questions. And I think in general, what we like to say is that you go into these expecting to answer this host of questions, and you may answer a few questions, but basically what you get out of that is new questions. Okay, we learned this, so what's next? And trying to advance the knowledge in that given field is really how these operate.
And I know that we offer, especially maybe some of our faculty on campus have gone down to see your labs underground. Do you have anything for people in the public to go down and see? Is that an option, or is there a process to get down there?
Unfortunately not right now. I really wish we could. We do have a surface tour that's run through the visitor center that's really quite good. But with the construction activities, and we're in a kind of in a rehabilitation mode with one of our shafts right now, the Yates shaft, and doing a lot of heavy maintenance there. And so we really don't have the bandwidth to take down many visitors right now, unfortunately. I really wish we could.
I have another question for you. This one is from Anthony Renley. I hope I said your name right, Anthony. As someone who spent some time down at the Davis site in the early 90s, he needs to ask, there was this 100,000 gallon tank of perchloroethylene. Is that tank still there? Or did they drain it, or did they flood it? Do you have any idea what happened to that?
It was drained, and for a period of time after Homestake had to turn the water pumps off, it was underwater, under about 300 feet of water. And then before we rehabilitated and overhauled the Davis campus, that tank was cut out. If you go up to the visitor center, one of the main main structural supports for the tank is now a sculpture right next to the visitor center. So you can see part of it, but the remainder of the tank is still underground in a safe location.
Thank you. I have one here from Jake. He would like to know what happens to the excavated ore.
So all of the rock that we're excavating, it either gets left underground, we'll put it into a space that maybe was mined in the past that's no longer being used. For smaller excavations, that's what we did for the excavation of the Davis campus. For the LBNF Dune project, we just simply can't put that much rock underground efficiently. And so, as I mentioned earlier, it's being conveyed over to the open cut and placed there in perpetuity. We have restrictions on mining. When Homestake donated the property to the state, there were specific provisions that we were not able to mine commercially. I would say, kind of given the current price of gold, I think if we found anything, they would be happy to take our phone call and talk more about it. But in general, the areas that we are excavating, there's a reason no one excavated there before. Like the LBNF Dune area, that rock mass is called the Poor Man, because there really is not any gold in that location.
Thank you. And I have one more question out there. This is from Taryn. Was an on-site air separation plant ever considered for the enormous supply of argon needed for the project?
There was. I wasn't a part of that, but there was a trade study completed between establishing a standalone plant and trucking that in, and the decision was made to truck it in. So
excellent.
I know. Yeah, I know there's a cost benefit against either, both options.